So my name is Omer. I'm from LinkedIn. And I'm going to talk about SPDY, which is the faster version of HTTP. So before I start, how many of you have LinkedIn account? Oh, quite a bit. How many of you have been endorsed for a skill you never possessed? Okay. How many of you decided to acquire that skill afterwards? That's a revolutionary thought. Okay, so we are here from LinkedIn. My name's Omer. I lead the traffic infrastructure team. Together with me is Brian Geffen, who'll join me for live demo and Q&A by the end of this talk. And if we're good, let's start. So as I mentioned, I'm leading the traffic infrastructure team, and every time I say that we have a traffic infrastructure, everybody says, what does that mean? And what it means is that LinkedIn has become big enough so that we need to start caring about delivering our own static content to our users without relying too much on third-party providers. Which is not really news because every big company of the size of LinkedIn is doing that already. But this time, LinkedIn has crossed that boundary of becoming an innovator in traffic, and this is why we have formed this team. And by the way, we are hiring. Having said that, let's start talking about HTTP. So HTTP is a hypertext transfer protocol, which is basically a protocol for transferring text. It was anybody here from Project Xanadu? Xanadu people? You're from Xanadu?
I've heard of it.
Oh, you heard about Xanadu? Okay. There's at least one person who heard about Xanadu. So Project Xanadu preceded, or at least started before HTTP was born, and has successfully delivered its first deliverable in 2014, making it the longest running project in the history of computing. And the idea of Xanadu, which made it to HTTP, is that there's a newspaper and there's lots of text, and people would read that text and they would ponder about what they read, and they will consider the meaning of it, and every now and then they would find that hyperlink and they will jump to another portion of text, just like in New York Times you'll find that continued on page F16. So that was the basic idea of HTTP, lots of text, person taking their time reading the text, and therefore latency of transfer not really important. What's important is the semantic complexity of the information that's being presented to the user, which at the time was a fairly revolutionary idea. Except that today, HTTP is being used to transfer everything, and lots of it. And this breaks the very fundamental assumptions of HTTP. If you remember, HTTP runs on top of TCP, and because HTTP was built to transfer large portions of text, every request of HTTP is supposed to be independent of each other. So up until HTTP 09, every single request required creating a TCP connection, sending 3 packets, then sending data, then sending another 4 packets just to say goodbye. Which was fine when the client time was long, but today, I've been told there's a laser pointer, but today, sending that amount of data over the ocean is just wasteful. But the story doesn't stop there. HTTP is getting obsolete in many, many, many ways. And let me look into those ways and let me explain what has been done to revamp the HTTP. It might be confusing that I'm talking about SPDY and comparing that to HTTP, but in fact, SPDY is the next version of HTTP. HTTP 2.0, which will be released early next year, is based on SPDY. So I'm going to use words SPDY and HTTP 2.0 interchangeably in this talk, but probably I'll use SPDY because I like that word better. So first of all, the first challenge with HTTP is actually challenge with the browser. Because we have to create a TCP connection for every burst of packets, we need to keep a connection pool to run multiple requests at a time. And browsers typically run out of that connection pool. What happens is that the browser will send the packets, and then there will be no more connections to send the packets, so the browser will start waiting. So as you can see here, the browser should have used only 22 milliseconds to get the data, but it was waiting 3 times as much just to get a connection, just to get the thread to pump the data. The other challenge with HTTP is coming from the fact that HTTP is using TCP, and TCP has been built to maximize bandwidth of the underlying physical connection. And before long, slightly after dinosaurs left the planet, but before HTTP was born, TCP used to flood every single router on the planet. And then the congestion control was introduced so that TCP would not destroy internet. And the idea with congestion control is that TCP will ramp up slowly to use every available bandwidth as opposed to theoretically available bandwidth. The catch is that HTTP connections are short-lived, so HTTP never is able to get away from that congestion control window, which basically means that every HTTP connection will be slow. Additional challenge with HTTP is that in our reality, there's a base page and there's lots of resources linked to that base page, and the browser will be required to parse that base page before getting the resources, which makes sense if the server never knew what the resources should be, except that server does know, because the resources are on that server. So instead of sending those resources to the browser and then letting the browser to parse the base page and to figure out how to render those resources, browser waits and waits. And the additional challenge with HTTP is the compression of headers. HTTP never compresses headers, which makes perfect sense for long newspapers. There's lots of body, there's a little bit of headers. And it doesn't make any sense for today's realities where we're transferring small GIFs, small PNG files, small CSS files, and the body is smaller than the header. Because the header contains all the tracking information, all the cookies, all the options, except encoding this and except transfer encoding that. And what happens is that the header is bigger than the body to start with, and then we do not compress the header. So we're transferring those headers. What's even more exciting is that we are transferring same information over and over and over and over again in those headers. Because if the user agent is Mozilla Firefox, and I'm starting to use LinkedIn.com, it's highly unlikely that I will change my user agent while browsing LinkedIn.com from the same browser. I may, especially if I'm using Opera, I probably would, but unlikely. So, SPDY. So far, so good? Anybody thinks that they have reached the wrong talk? Okay. So SPDY. SPDY is based on SSL. It is using next protocol negotiation to handshake together with SSL negotiation, which means that for long-lived sessions, we don't need to renegotiate the SSL for every connection. SPDY supports multiplexing, which means that we don't really have to open a new connection to get a new resource. We just can reuse one connection and start streaming lots of requests. SPDY will use a protocol which is called framing, which runs below HTTP level to split those requests into chunks, to multiplex those chunks into same stream, and to associate requests with responses. All of that is happening below the level of HTTP so that clients don't really feel any difference. What makes it even more exciting is that SPDY is secure in the same sense that SSL is secure, which really means that we know how we believe that we know the identity of the server. What that means is that we don't need to redistribute the certificates. We can use the same certificates, and we use the same trusting authorities. So SPDY is a drop-in replacement for HTTP, both from the client perspective. It supports the same ideas of I have a request, I need this resource. And from the ecosystem perspective, which means that we don't really have to teach the world how to use SPDY. SPDY also supports that fancy thing which is called server push, but really it means put that thing into browser cache. This is great for sites like LinkedIn, where there are lots of recurring images. So instead of saying, hey, this is your base page, but Mr. Browser, please start parsing the page. Oh, you have parsed the page. You need those 3 GIFs. OK, we'll send them to you. Instead of that, the server, LinkedIn.com in our example, can proactively push those images into the browser cache. And the moment that the browser will decide to use those images, oh, they're in the cache. How convenient. And probably the best feature of SPDY is that we do not repeat ourselves. This is the DRY principle in practice. We are reusing the headers that we have sent, and we are not repeating the information that didn't change. So if I have negotiated the user agent to be Mozilla, and if I'm not intending to change that user agent, SPDY will make sure that this particular header will be never sent. And then it will compress whatever headers that are sent. So this is more or less summarizes the features of SPDY that we found attractive compared to what we used before. I'm going to start talking a little bit more about what we did with those features, but before that, any questions?
So there is a single connection between client and server. We are making it susceptible to DDoS attack or something. How are we avoiding that?
Let me repeat the question. Since there is a single connection between client and the server, are we making the server susceptible to DDoS attacks? To a degree, yes, it would be possible to create lots of connections and to make them really, really slow. And in this way, we will be able to drain the amount of server threads on the combined pool of all the servers that we have. So I do believe that it would be possible to start depriving our servers from those connections. Fortunately, that kind of DDoS attack is fairly easy to detect, because if there is an activity on the browser and the connection has terminated for some reason, the browser will reestablish a connection seamlessly, which basically means that if we have lots of dormant connections, we, as LinkedIn.com, can implement a policy of terminating those connections. Now, the difference between this and what we have in HTTP today is that HTTP forces those connections to be terminated after 15 seconds of inactivity. This is the keep alive window. Whereas in the case of SPDY, that particular limit can be tuned to the particular level of threat that the organization is perceiving. If there are lots of attacks happening, well, that window can be trimmed down. If you are safe, then hey, why? Should I continue? I will. So let's take a look at the typical LinkedIn or Facebook or Google or what have you page. There is a base page, which is the HTML page that's being requested, which has lots of references to things which we call static content. It is static because typically it doesn't change. It's the same content over and over again, and there's lots of it. Images, CSS files, JavaScript files, media files, lots and lots and lots of content that make the web attractive and dynamic and very different from what we used to have in '86 when HTTP was used only for text. So all the non-text, aka static content, represents the majority, the lion's share of the traffic that we are sending over to the browser. And since SPDY is that promising, our first idea was to use SPDY for static content, because that's what the low-hanging fruit that we wanted to pick. And before we have adopted SPDY, we used to, well, we still do in certain cases, we used to rely on CDNs to deliver that static content to us. So the base page was delivered through LinkedIn network stacks, through our points of presence, whereas the static content, which I craftfully marked with blue, so that it will be confusing with data centers, which are also blue. So the static content will be delivered through CDNs, which will pick it up from our origin cache servers, which are spread all around the world. And in that way, we are storing lots of our static content somewhere in, I don't know, Singapore or Gainesville or somewhere, whenever those CDN caches are located. And the thing about CDNs is that they tend to be fast. Some of them are faster. Some of them are just fast. They tend to be ubiquitous. Some of them are more ubiquitous. I heard that Akamai has 1,027,000 of edge servers around the globe in 87 countries. Some of them are prefer to be smarter and not that ubiquitous, but still they're fast. But the real challenge with CDN is that they tend, and again, I'm using the word tend because there are innovators in the field of CDN. They tend to be fairly rigid and fairly inflexible when it comes to delivering content which is falling outside of the expected response that they know how to cache. For example, Akamai is refusing to add a veri header for us. That's plainly refusing, because they cannot. I'm not blaming them. If I were Akamai, I wouldn't be able either. But they're not built for that kind of flexibility. And on the other hand, if you take a look at the map of the world where all the continents are are present, but the countries are removed, and you look at the locations of those CDN edges, you'll see that the world is being attacked by some sort of CDN. So our POPs, which again are blue, are small, but they are located in highly populated areas. CDNs, on the other hand, are located pretty much everywhere. I doubt that there's a CDN in Kathmandu, but there's for sure is a CDN somewhere in Altai Mountains. And that will be probably Akamai, and they will probably not change their headers for us. So one of the benefits of working at LinkedIn is that we have the whole world to play with. So we decided to play a little bit, and we decided to set up an experimental SPDY point of presence somewhere near Detroit or Chicago. So Brian, how long did it take you to set it up? 2 days. So in 2 days we had that new shiny toy, and we started to collect data. So what we did was creating a new DNS record, diverting part of the users to the DNS record. For that DNS record, we have instrumented our point of presence with a ATS plugin that rewritten the static content URLs with SPDY URLs, redirecting them to the same ATS point of presence, which happened to run SPDY, terminated SPDY, and compare the performance. Here's what we've got. We figured out that, hey, SPDY is speedier. Surprise. But we also have figured that the relative performance of SPDY is decreasing with the distance from the POP, which makes sense. We also have found that for SSL connections, SPDY is way faster than SSL and HTTP. Reason for that is that SPDY is using same TCP connection over the longer span of time, and it makes single SSL negotiation instead of repeating the same SSL negotiation over and over and over again. Well, with those results, we have decided to come back to our reality and to augment it a little bit. So instead of relying entirely on CDNs to send our static content to users, we have decided to start with using SPDY for densely populated metropolitan areas where SPDY would be faster, and to rely for on CDNs for the second tier static content delivery for areas where there are not a lot of users. Now, this decision was actually a business decision because majority of LinkedIn users, power users, are living in densely populated metropolitans. So obviously, those would be the users who would benefit the most from higher speed connections, from new application possibilities that SPDY opens up with server push and what's not. So we decided to start there. And that plague that eats the world has changed its shape. So now our POPs are covering much more population, and we're relying on CDNs for places like Cairo or, I don't know, what is that in Africa? I think it's East Rhodesia. So for places like Rhodesia, we're using CDNs. I think, by the way, that this is the same approach that Fastly is taking, with fewer POPs, faster POPs, more capable POPs, but not necessarily the huge price of maintaining thousands and thousands of servers, thousands and thousands of network locations, paying the electricity, negotiating the placement of servers within the rack, and what's not. And what it means that now our POPs include a SPDY termination stack, an origin cache for CDNs and for SPDY termination, because we're in fact using our origin cache to drive the static onto the user, either through SPDY or through CDNs. And we are ramping SPDY in production as I speak. And the bottom line is that SPDY is here. Soon will be called HTTP 2.0. Currently, not all CDN support, not every CDN supports SPDY. Some of them are starting to experiment with that. In the near future, I expect that all CDNs will support HTTP 2.0. There's no other way. There's that or getting out of the market. And then internet will be faster for everybody. So I think that at this point, I'll invite Brian to run the live demo together with me. And then we'll go to the Q&A. Before we go to the live demo, I would like to highlight the fact that we're still hiring. Okay, so this is me. And this is my profile. Well, this is what's going on the wire. As you can see, our static content, for example, this PNG image, is being delivered through SPDY. And if you go to the net internals page, you can see that we're transferring quite a few frames over SPDY from LinkedIn.com. Let me refresh. You can see that we have received 455 frames on the same connection. HTTP would probably would have required a few dozens TCP connections to deliver same amount of information. And it would probably force us to renegotiate SSL on every new TCP connection. So here it works fairly smoothly. One caveat though, right now we are still in the process of ramping SPDY to everybody. Our policy at LinkedIn is to always ramp new features carefully over the population, which means that some of you might not be seeing SPDY in the Chrome right now. If that's the case, give us some time. Within a few weeks, we will be transferring all of our users who happen to be within a certain distance from our pods to SPDY. Users who are outside of that proximity zone will still be using HTTP and HTTPS, and therefore getting the static content from CDNs. The proximity zone is being determined by performance, so we're trying to find that little line that makes SPDY better, and we're adjusting that. And that's also the reason why we are still transferring our base page through HTTP and not through SPDY. That makes the ramping much easier, because once we have the base page, we know where the user is coming from, locale, geographic coordinates, and what's not. Our next step would be to renegotiate SPDY through NPN. That would give additional performance boost, because we'll be able to send the base page through SPDY. It will rob us from the ability to finally ramp users into the SPDY. So we're waiting with NPN negotiation until the point we will be confident that we have all the capacity, we didn't make any snafus with a number of servers or anything like that. I think that's about it for the demo, and I'm running a little bit faster than I planned, so we have more time for questions. Yes.
How much do you guys actually use the preemptive pushing?
We are not using it at the moment. We are planning to start using it somewhere around the end of 2004 for our mobile platform, and around the first half of 2015. Yes, 2004, 2014, of course. Somewhere in the first half of 2015, we are going to use it across all of our sites, desktop and mobile, for the common elements of the navigation and such.
That's interesting you guys are starting on mobile because aren't there like device constraints on how much you would want down, or are you starting with mobile because you're going to like push the small amount of stuff down?
We're starting with mobile because mobile devices are more prevalent at markets where performance is slower. India, China, what's not. And SPDY has better performance characteristics compared to HTTP if the latencies are higher. That does require us to place a POP in those populated areas. But once we do place a POP, then the population of our users benefits much more from SPDY. So this is our primary reason to start with mobile. Although from the technological perspective, it would be much easier to start with desktop, just because we have a single version of desktop and not, desktop for Android, desktop for iPhone, and what's not. Yes?
So when you roll it out into production, so that way CDN and SPDY, best practices, that even goes up or directly serve traffic.
So if I heard the question correctly, when we ramp into production, will we utilize both CDNs and SPDY, or will we wait until CDNs will fully support SPDY? We are not going to wait. We are going to build our own infrastructure for serving SPDY from our existing POPs. And as CDNs will catch up with HTTP2 support, we'll utilize that. We are not going to wait for Akamai to catch up. We just don't want to use another year or so. Yes?
So looking at that diagram, the SPDY connection terminates with the load balancer, and the load balancer is talking to the back end, not using SPDY?
Let me repeat the question, and let me also get the diagram. So the question was whether, looking at the diagram, SPDY terminates at the load balancer. Well, yes and no. We do terminate SPDY at the edge, and once we have terminated SPDY, it's plain HTTP. It's not HTTPS, it's plain HTTP going to the data center at the moment. The reason for that is that this is the simplest way to start getting benefits from SPDY for us. And this is the yes part. The no part is that it's not really a load balancer. It's a two-layer scheme where first we do DNS round robin based on the BGP zoning, and then we use what we call sticky routing. So what happens is that any member will get to a POP, some POP, and that POP will be determined by the BGP rules. And then that POP will determine who is that member and redirect that member to the data center where that member's data is located. So it is sort of a load balancer, but it's not what you would call a layer 4/7 intelligent application switch or whatever load balancers are called now. Yes?
When does the underlying connection get terminated for SPDY?
So the question is when the SPDY connection is getting terminated. The SPDY connection today is being terminated at the edge, which means that the moment the SPDY request is being routed through DNS to a point of presence of LinkedIn. We are terminating that connection, and we are communicating the data. We're demultiplexing the stream into many HTTP streams. We are keeping very large pools of HTTP connections at the edge, so that we don't have to re-spin the TCP connections for those connections.
And when does it get disconnected?
Oh, when it does disconnected, sorry, I misunderstood the word terminated. So whenever SPDY connection is being dropped, either by server or by client, and if the browser still needs to get something through SPDY, the browser will re-establish a new SPDY connection to the same server. So there will be additional performance hit because a new TCP connection has to be established. The congestion window has to be reopened, and SSL has to be renegotiated. However, this doesn't happen as frequently as it happens with HTTP. So this is the answer. Anybody else? Oh, okay.
I was asking, talking about sort of SPDY in the browser, but I think most of us probably use HTTP for applications, endpoints, APIs. Are you guys doing anything internally to make request instrument APIs faster?
Let me repeat the question. This speech is focusing on SPDY in the browser, but SPDY can be also used from internal APIs. The answer is that right now we are focusing on the browsers because this gives the most cost-effective benefit to our users. Our next step is to stop terminating SPDY at the edge and start utilizing new versions of Jetty, NetTI, and Java, who are supposed to have HTTP2 support natively. And that would allow us to introduce SPDY semantics to the application, which means that applications will be able to proactively push data to the browser, making the LinkedIn site much more attractive, dynamic, and faster. It will also allow us to demultiplex internal requests within the data center using fewer TCP connections. So we are planning to do that. It's not in our roadmap for remainder of this year. But yeah, absolutely. And the second question from same area?
So how do you segregate users who are sort of close to the platform?
Let me repeat the question. How do we decide which users are close to the POP and which users should be using SPDY versus CDN? For that, we are using the GeoIP database, and we are determining the geolocation of the user, which is, we all know that it's incorrect, outdated, but statistically it is mostly accurate. Once we know the geolocation of the user, or once we know with high probability that the user is at certain geolocation, we calculate the distance between the POP and the user. And if the distance is lower than the threshold that we discover empirically and maintain as we go on, we serve SPDY URLs from our base page versus HTTP URLs from our base page. Starting from that, the browser will take care of using SPDY or using HTTP. This is also the point where we decide whether the browser supports SPDY. Today, SPDY is supported by Chrome. It's going to be supported by IE 11 is going to be supported in Firefox, but there are many versions of browsers out there which do not support SPDY yet. Since LinkedIn is very much user-centric, we do not believe in serving only the cutting-edge population on the planet. So we are going to continue supporting HTTP to the point where there will be no LinkedIn users who are using HTTP, which, as far as I know, will never happen. There always will be that guy on Windows 98 running Internet Explorer 3.2 with JavaScript disabled. Any more questions?
What percentage of traffic do you estimate that you serve using SPDY?
What percentage of the traffic we estimate that is being served using SPDY today? So our estimation is based on the assumption that we are fully ramped. Right now we are not fully ramped, but once we are fully ramped, at this point, we are going to serve something like 30% of the traffic worldwide multiplied by 40% of the browser adoption. So we are looking at something about 10%. And of course, as our capacity grows and as browser adoption grows, this number will grow as well. Yes?
Can you upgrade an HTTPS connection to a SPDY connection?
HTTPS connection to a SPDY connection. I believe you can do it through the APLN SSL upgrade.
So once you know that a user is within your range and you would like, and the POP would like to communicate with the user over a SPDY connection, I mean, at that point, you will have to upgrade the connection to SPDY connection.
Yes.
Okay, and how do you determine that this connection can be upgraded to a SPDY connection?
If it cannot be upgraded, then the protocol upgrade will fail.
Okay.
That's handled by SSL semantics.
Okay.
We will offer the next protocol. SSL will say, hey, I don't know what you're talking about, sorry, and we will bail out. Yes?
So one of the nice things about HTTP is the plain text nature of it, which makes it easy for dynamic tracing or for packet capturing and inspecting it. You guys found that going to SPDY and it's more with everything compressed, the implicit headers, and with the local frames actually observing when things go wrong, and what techniques have you guys developed for that, or how's that experience been?
So the question is, given the fact that SPDY is much more efficient in using the connection, it is also making troubleshooting harder because it's not transferring as much information that can be used for debugging. And what are we doing about that? So our first strategy is to use the browser before the HTTP level semantics are being transferred into SPDY. So that allows us to focus on whether the correct headers have been sent by the browser. We are also using Wireshark to inspect the SPDY connection by itself, but that requires us to keep track of all the header elimination by ourselves. So as of now, we are using the combination of Wireshark browsers and SPDY clients to debug our connections. And the browser is fairly helpful in that because it can transparently give us the information about the SPDY from different stages of encoding. Yes?
Just a follow-up. So what do you do when you don't have, because most of your users, obviously you don't have access to their browser, so what do you do when you don't have access to the browser? I mean, I presume that there are a lot of cases that you have to debug, which are the case that a random user on LinkedIn is hitting an issue, and you don't get the luxury of necessarily being able to reproduce what's happening.
the question is, what do we do when a particular user is having problems and we cannot reproduce using, and we don't have the way to reproduce what's going on? At the extreme case, we will impersonate as the user, of course, given users permission to do so, to precisely reproduce the behavior. On the less extreme cases, what we do is intercepting the data at the edge as we are transcode SPDY to HTTP. Since the transcoding is one-to-one, we do have all the information in HTTP form. It does not allow us to focus on SPDY framing protocol though, and this is where we're using Wireshark. On that note though, I do believe that there is a room for development of a little bit more automated and effective techniques for troubleshooting as we are going to grow SPDY and have it adopted in a wider fashion.
Another thing about troubleshooting SPDY connections over SSL is as long as you use a cipher that doesn't involve perfect port secrecy, you can use Wireshark to then encrypt the data with the private. So if you're willing to disable perfect port secrecy for a select number of users to troubleshoot, you can do neat things after the fact. Whereas if you are using perfect port secrecy, most people should be using it for your SSL cipher, then even with the captured data, you can't do much because that's the point of perfect forward secrecy. So if you're willing to change your cipher selection on a per user basis, you can do some interesting things with Wireshark captures.
Thanks, Brian. So we're getting close to the end of the session. We probably have time for 2 or 3 more questions. Anybody from this side of the hall? Okay, I think we are done. Thank you very much for attending.